We are now at a point where we can talk about the Arrhenius equation. This is the equation that allows us to determine and calculate the value of the activation energy. And I'm going to show you two versions of it. I'm going to show you the two-point formula, which is the one most generally presented in general chemistry books. But then I'm also going to show you the linear equation, the actual relationship that you tend to use to derive the activation energy. And both of them are the same equation, except that the two-point formula will present itself in terms of two data points. All right, now Arrhenius, which is a picture of shown right here. I think they caught him by surprise on this picture. Um, you basically have a relationship between the rate constants of the reactions and the temperature of the reaction itself, specifically the natural log of the rate constant versus the inverse temperature in Kelvin yields a linear equation for which the slope contains the activation energy divided by R. Alright, so what we're basically going to do, and what Arrhenius basically did, is he was able to make a correlation to the fact that the rate constants are changing with temperature, but that change has a relationship in and of itself. Alright, so this is the idea. The ln of k versus 1 over t gives you a line, a linear plot with a negative slope. And that slope corresponds to the negative of the activation energy divided by R, where R represents the gas constant, 8.3145 joules per mole Kelvin. Alright, now if you write this as a linear equation, basically what this line will correspond to is ln of k, which is the y value, time equaling the slope, which is negative activation energy over R, times x, which is 1 over t, plus the y-intercept, which we're just calling b. If you solve for the y-intercept, then what you end up yielding is y plus activation energy divided by RT, which equals the y-intercept. Now the intercept itself is not going to change. Technically it's a constant. And so if you pick any one data point along this line, you'll have a data point that equals basically ln of K1 plus activation energy divided by RT1. But picking a second data point is also going to have to equal the y-intercept as long as you add the ln of K by the activation energy over RT for the corresponding temperature and rate constant values. And so what this tells you is that the ln of K plus the activation energy over RT terms equal each other. And if you basically subtract the ln of K from both sides and subtract the activation energy over RT2 from both sides, you're going to end up with this relationship right here. And lastly, when you subtract two logarithms, you can basically combine them together as one single log, whereby the insides of the log are being divided from each other. Over here, we have activation energy over R, which is a constant between the two fractions, so we can factor it out. And so now we get a more traditional format to this equation, which basically, if you just move what's on the right side to the left and what's on the left to the right, you end up with a two-point version of the Arrhenius equation. ln of K2 over K1 equals negative activation energy over R times 1 over T2 minus 1 over T1. This is the equation that you will use if you have two data points. And with those two data points, you can approximate the activation energy. Alright, so as I kind of implied at the beginning, the value of R, I didn't imply it, I literally say it. The value of R is 8.3145 joules per mole Kelvin. The temperature, by the way, has to be in Kelvin, much like any gas laws. The activation energy will have to be reported in kilojoules per mole. So when you use this equation, you just have to remember to change the joules of the R constant to kilojoules in order to end up with kilojoules per mole for the activation energy. Alright, so let's take a look at an example. We have rate constants for a reaction, 7.78 times 10 to the negative 7 and 3.46 times 10 to the negative 5 at 273 and 298 Kelvin respectively. We're going to use that information to determine the activation energy of the reaction. So because we're looking for the activation energy, we have to deal with the Arrhenius equation. And so we start with the format for the 2-point equation. And what you want to do, or what I would recommend that you do, is plug in the values that you have as of now. You know that K2 is 3.46 times 10 to the negative 5, so 298 has to be T2. So notice that I have 298 for T2. 273 will have to correspond to T1, which is in association with K1. Alright, so as long as you place everything in the correct place, everything's going to work out fine. Otherwise, you might end up getting some, rather weird results. Alright, now, what I would recommend that you do is divide the two exponential numbers inside the logarithm, press enter in your calculator, and then take natural log of that answer. And basically just write down the value. And over here, what I recommend is that you open parenthesis, input 1 divided by 288, close parenthesis, subtract from that, open parenthesis, 1 divided by 273, close parenthesis, and press enter to get this value right here. And so what you'll end up with is 3.79489 for the logarithm and negative 3.073 times 10 to the negative 4 for the parentheses on the right. And here the problem actually becomes a lot simpler to solve, because all you have to do now in order to solve for the activation energy is multiply both sides by negative 8.3145 and divide both sides by negative 3.073 times 10 to the negative 4, which is what we're doing over here. Notice that the kelvins cancel out, and what you end up with is joules per mole. At the end, all you have to do is divide this answer by 1,000 in order to get it in kilojoules per mole. And this is the traditional way of using the Arrhenius equation, the 2-point version of the Arrhenius equation. Now, the linear format of the equation, I've already shown it to you, is simply the equation of the line. ln of k equals the slope times 1 over the temperature plus the intercept, right? So this is your y equals mx plus b equation. And typically you have to be given some data points in order to use this particular format of the equation. So for instance here, notice that I have some values given for my rate constant. I have some temperature values in association with that. So I could use the 4 rows, right, the first 3 and the last one, for which I have rate constant and temperature data. And using Excel or some other program, what you will have to do is change the temperature from Celsius to Kelvin, then change the Kelvin temperature to inverse temperature, so literally divide the temperature from 1. And lastly, you have to take the value of K and basically apply the natural log to it. Alright, so you'll have new values. So either you could use Excel, you could use Logger Pro, or any other program that you may like. But the idea is that you have to get the ln of k to plug in as your y values for the Arrhenius equation, and you have to get your inverse temperature to be input as your x value in your graph. So if you plot ln of k versus 1 over t, you're going to get a line, and this line has, there we go, this line has the following slope and the following y-intercept. Now the thing to be remembered and to be kept in mind is that the slope represents negative activation energy over R. So literally this 30,320, or rather the negative 30,320, has to equal negative activation energy over R. And what this means is that if you multiply both sides by negative 8.3145, which is the value of the R constant, the negatives will cancel out, the K's will cancel out, and you're going to end up with a value which is in joules per mole. And once again, divide this value by 1,000, and you'll end up with your value in kilojoules per mole. So this approach is a lot more simplistic and a lot more accurate than the 2-point equation approach, but it does require that you have a table of data for rate constants and its associated temperatures. Without that, the best you can do is use the 2-point equation. All right, now another thing that we could do, of course, is since we have the y equals mx plus b equation here, we could actually calculate the rate constant at some other temperature. We could calculate the rate constant at 69 degrees Celsius. And the tricky thing about this is that you got to remember that what you have here in terms of temperature is temperature in Kelvin. Not in degrees Celsius, but in Kelvin. And not only that, the x value of this equation is not the temperature, it's the inverse of the temperature. So what you need to do is not only convert the degree Celsius to Kelvin, but you have to divide it from 1 to get the value of x from this equation. So x is literally 1 divided by 669 plus 273. Alright, so you get the 1 over 942, which gives you now a new value, 1.06 times 10 to negative 3. This value of x can then be inputted into the y equals mx plus b equation that we obtained from the regression, the linear regression. And when you multiply negative 30,220 by 1.06 times 10 to negative 3 and add that to 29.35, you get the value of y, which is negative 2.837. Now, many people make the mistake at this point to literally just circle that as the answer and say the rate constant is negative 2.837. And they kind of forget about the fact that y is not the rate constant. According to the equation here, y is the natural log of the rate constant. So basically, what you have to do is now associate negative 2.837 to the ln of k, which is literally what the y represents in this equation. And you have to take the anti-log of the natural log, which is the same thing as saying that you will raise e to the power of negative 2.837. And when you perform that operation, you will then find out the value of the rate constant. Now, in this particular case, you can tell that something is amiss with the value you got here for y, because the rate constant is meant to be a positive number every single time. You're never going to have a negative rate constant. It will always be positive. It could be small, but it will be a positive value, right? So that kind of gives you an idea that maybe you're dealing with the ln and not the actual value of the rate constant. All right, so that concludes the discussion of the Arrhenius equation. What you should get from this is that there is a procedure involving the rate constant and the various temperatures of the rate constants to derive the activation energy. And this comes in the form of the Arrhenius equation. In the next video, I'm going to show you how you end up determining the rate constants themselves. All right, so see you in the next video.